Hi guys, trust you're all doing well. Welcome to my YouTube channel, CPM Stack with Oluwole. Let's get right into it. In today's module, we'll be looking at system design for API first platform. In our last module, we look at the concept of API as a product. In this module, where we discuss types of APIs, right, and your role as a technical product manager or a product manager in helping looking at your company infrastructure today, your existing services, features, and tailoring it and matching them with a need in the market as of today, where you can open that system up or you can open up that service or infrastructure to developers, businesses, companies, partners for consumption. Now, let's assume you've decided to open up your system. There are certain things you need to be aware of, and these are things that are outside your control. First thing, you can no longer determine the amount of traffic that will be coming in at any given time. Traffic becomes very unpredictable. A failure in one client or in your service can affect multiple users, and this can also directly impact the user experience across your product or across your industry today. Latency, how fast or how responsive your system is, directly also impact the user experience. The amount of traffic your system can handle also directly impacts the numbers, how stable your system will be really, right? In essence, you've seen scenario where you're trying to make an API call to some platform, and for one reason or the other, you're not getting response or you're getting downtime. Hence, this is very important for us to start discussing around system design. The way you design your system will determine how your platform will perform in the market. And don't forget, one thing that is very important across all products, whether API, customer facing product, is experience play. You want to give your customer the best experience out there. There's a mindset around product today that goes around, if you cannot beat what exists in the market, don't even bother building. So for you as a product manager looking at building API related product, it's important to have some of the things we'll be discussing in this lesson in mind. Take them seriously. This will help determine your product experience and if your product will even lead the industry in whatever this area or field you decide to play in. To help you better understand the concept of system design, we've split this module into 5 major sections. First, we'll be looking at fundamentals of system designs. This is where we'll be looking at what system design means, what it means, why it matters. Secondly, we'll be looking at core components of system designs. In some of our previous modules, we've discussed concepts around monolithic architecture, microservice type of architecture, database, where you're looking at SQL, MySQL database, and what best database works for different types of application. We'll be revisiting some of that, and we'll also be adding to some of them. We'll be adding to looking at additional concepts in this in that section. Thirdly, we'll be looking at scaling strategy. Fourthly, we'll be looking at database. In some of our last module, in our previous modules, we've discussed the concept around how every API you call or every button you click on a website is sending certain information into the database. It's either creating, it's either deleting, it's either reading, or it's either updating an information in the database. So when you have millions of customers using your customers at almost the same time, it's important for you to have your database query optimized in a way that it's able to perform. And lastly, we'll be looking at latency and throughput. These are a new concept that I'm introducing in this course. However, in the later parts of the course, you get to understand what they mean and why it's important for you as a TPM to understand this concept and to track them. Use them as a metrics for managing and monitoring your API platform. Oh yes, this session is going to be a long one. So Let's get your popcorn ready and let's get right into it. So let's start by looking at or defining what system design is. According to my definition here, system design is the process of defining architecture, component, the interface, the data flow of your system or your platform or your API product to meet both functional requirements and non-functional requirements. What does that mean? Let's start by looking at, on a high level, what each of these components means. Architecture literally speaks to how you organize your platform, right? What talks to what, where's the entry point, how is the database, literally how you organize your platform or your system in its entirety. When you look at component is the little boxes where you are able to like identify, "Oh, this should work for this is work for this." Maybe you're building a house, you can say, oh, the window should be here, the door should be here. These are fundamental components. And in terms of like system design, those fundamental components are, you have them as application server. We'll be looking at application server, we'll be looking at database, you'll be looking at entry point, load balancer. And thirdly, interface is your mobile application. How is the application being accessed in the first place? Don't forget, we said you can access application whether on the API level or on a product level. I mean, when I mean product level, customer facing product level now. And data flow. This is where we look at concept around your database type, how to scale your database, how to also we'll also be looking at something called indexing, caching mechanism. We'll be discussing all of this at length. In our definition of system design, we mentioned something around functional and non-functional requirement. What does this mean? When you look at functional requirement, this is where we are talking about, you are describing, and this is what most PM does today, where they write PLDs to describe how the system should work, right? Where you are telling the system how it should work. However, this is in the case of API product, right? We are looking at building, I think one thing we should have in mind is, we are building this platform as an API solution. So when I say you are building product, have API in mind. So as a product manager or as a TPM, you're describing how your system should work. That's the functional requirement. A typical example is you want to build your system in a way, or you want to open up your system in a way that when developer calls your payment API, they can use it for payment processing on their own application, be it a e-commerce app, a telemedical platform. You just want to expose an API to them that can allow them or enable them collect, receive money from their customer. Secondly, what is non-functional requirements? These are the kind of requirement this is where you have to go into writing technical documentation, where you are labeling or laying out how the system should work, what success means, identifying metrics. As a TPM, you will not design it. Don't forget that in one of the courses we did, we discussed around the roles and responsibility of an engineering or a technical product team. As a TPM, you might not be responsible for designing or even creating the architecture, but your core responsibility is to laying out what success means for each of these services you're exposing. A typical example is where you're saying every API calls, every time, no matter the amount of traffic, our API should respond within less than 100 milliseconds. You can also have metrics to saying that our platform, our API platform, should be 100%, maybe not 100% reliable, 99.9% reliable. It means that if customers try your APIs or try using your platform, the chances of them getting a successful response when they call your API should be significantly high. Every system out there today have some of these core components in their modern design. What does this architecture do? What does this is? And in reality, you have almost all systems. However, the way they have designed it might be different. But these are core things that will be in modern system design today. You always have a client. You always have a client section. And you also have an API gateway. This API gateway does two things. It can serve as a router. What I mean by a router is when the API takes in requests either probably from the API level, from the client level. It takes in that request and is able to understand what request is able to handle, or what application server is able to handle this request. So it sends that request to to the application server. Take for instance, you're trying to make a transaction. API router looks at the nature of your request, the payload, the information, the URL, and it sends that request. It ensures that that request goes to transaction service or transfer service. It doesn't send your request to transfer service related request to profile management request. API gateway is responsible for helping you ensure your request gets to the right application. Also, it also acts as the load balancer. Right? What does this mean? We'll be discussing this at a later time. But it acts as a load balancer where it's able to look at it's able to route traffic to the least serving application. What does this mean? You've scaled your application to having two major applications. The API gateway helps to look at it will route your request to the least performing or the least serving application. So you're able to get responses in real time. You don't have your responses or your request being queued because maybe service A is clogged up already. It ensures your request is sent to the application that can respond to you in near real time. We'll look at this at a later time in this course. On this section is where we have application server. The application server we can have it as payment, we can have it as invoicing, we can have it as ordering services. And lastly, in this section is where we have databases, where we'll be looking at we have two key things I would like you to take out of databases. We have temporary storage and we have permanent storage. Permanent storage in terms of you can still, however, you can delete your information. But we have temporary storage. Temporary storage is where data are stored in a certain place for a limited amount of time. This is where we'll be looking at caching, right? Some of the platform around that is Redis. And we have the bigger database, right, or the primary database. This is literally where your information is stored for reliability and consistency. You don't want to go into your app today and your name is Uluwole today. And when you're looking at it, you go into the app, you're finding Damilawi's name or you're looking at Regina's name. That doesn't make any sense. You will literally lose trust in such an application. So why is system design even important? What's the objective? Firstly, it helps you ensure that you build a system, a platform, an infrastructure, a product that can handle millions of customer requests concurrently. One of the things we discussed earlier is you are building this platform, you cannot determine how traffic will be coming in. That is the moment you decide to open up your system, that ability to decide or predict traffic inflow is out of your control. So you need to build a system. System design helps you to build a system that can handle high amount of traffic. I mean unpredictable amount of traffic. System design also helps to ensure that your API is able to respond to your customer in milliseconds. Once you start building API solutions or customers, when you start looking at competitive analysis of your API infrastructure that you intend to build, you realize that one of the major key metrics for you as a success or for your platform is how responsive your API is. Can it give me response in less than 50 milliseconds? You don't want to build a platform that takes about 60,000 milliseconds to get a response. Trust me, nobody will use your platform. Because number one, you're breaking the number one rule of product. You cannot give people what is lesser than what exists in the market today. Thirdly, one of the key goals of system design is to ensure that your system is able to scale efficiently and fail gracefully. What does this mean? traffic will not be the same at every given point in time. In the payment industry, we've seen that during salary week, yes, a lot of people tend to make a lot of payments. And when you start going into the midweek, you see transactional activities reduces over time. It means during payment period, salary week, your system needs to be able to auto scale, because it will see a spike in terms of numbers of requests from probably is handling 1 million requests on a daily basis. You'll see it go to about 50 or 100 million requests per second. So your system, you need to build a system that in a way that is scalable. It can build, it can scale, it can handle the amount of requests. Later in this course, we'll be looking at scaling architecture and scaling strategy. But as a system design helps you to identify how you can scale your system gracefully. We also spoke about failing gracefully. What does this mean? Failing gracefully means system design helps you to ensure you're able to build a system that can fail and still probably a request is not accessible. A request is not accessible, but it's still able to attend to other customer requests, or an app server is down, it's still able to route requests to other app server. At the end of the day, what system design helps you does is it helps you find a way of ensuring you have a system that is fast and that also reduce database load. Now we'll be discussing the core component of modern system design. Under this section, we will literally only be looking at event-driven architecture. In some of our previous modules, you can look at, you can visit them if you've not seen them before. We've looked at monolithic architecture at length. We've also discussed microservice architecture at length. In this area, we discuss the advantage, the importance, the use case, the benefit of building your system to probably fit a monolithic, a microservice, or an event-based type of architecture. In this lesson, we'll be looking at event-driven based type of architecture. We are looking at this right now because we've not covered it in the previous module, so it's important for us to cover it. Now, what is event-driven architecture? According to my definition here, event-driven architecture is the design approach where system components communicate by producing and consuming events instead of making direct and synchronous requests. What does this mean? You know where we've said that every button you click or every request you send via the API talks to a database. In the case of event architecture, this kind of architecture is not necessarily expecting direct API request, or is not expecting you to directly click a button. A typical example is you go into a store. Maybe you walk into a store or you decide to purchase an item online on an e-commerce platform. You see the item, you went through the process of from the item selection to inputting your delivery address to making the payment. What event architecture help you does is the moment it listens to that process being completed, when it shows you payments or purchase completed or purchase successful, it fires an event. That event is what triggers the email you will get the successful purchase of an item. Event architecture is what also helps you get SMS immediately you finish making a transaction. So it's not expecting a request. In the way the system is designed, it's only looking for certain attributes. So they have something they call event listener. So it's only listening for certain information or certain attributes. Once you get that information, it triggers certain things. It can decide to trigger SMS. It can decide to trigger email. It can also decide to trigger push notification. And this is the kind of architecture platforms like social media does. The moment you send a message, there's an event listener. The person you send the message to automatically gets a notification that, oh, the message has been sent to you. That's how it works. So you have platform that really does real-time tracking, uses this platform such as charts, notification, payment, and spot activities. When you put on your smart wristwatch today and you start running, The system, the application or the device in itself is listening to an event. It's trying to get an information. So it's knowing that this person at this particular point is looking at this person is running, or you're engaging in an exercise. So your system or your smart devices pop up to say, oh, are you engaging in this in an exercise activities? Let me help you track. That's how the system is known. You have been able to explain that concept very well. If you have any question, you can always let us know in the comment section. Thirdly, we'll be looking at scaling strategies. Before even going into the course, I want us to have a mindset shift, or something I think we should have that will help guide us before even going into this section. When you talk about scaling is not just applicable to database, it's also applicable to application server in itself. Please, let's have this in mind. It will come in handy later in this section. Under this section, firstly, we'll be looking at vertical scaling, scale up. What does this mean? According to my definition here, vertical scaling means making one machine stronger by increasing its memory size, the CPU, or the disk capacity. What does this mean? Let's bring it home. Actually, let's bring it home to something relatable. Take, for instance, you work in an organization that provides you staff bus. The organization used to have a strength staff of 15. So you have a boss that basically is able to cater for the mini boss you have today. You have that mini boss and is able to cater for 15 staff. As the company and the organization grows over time, the staff strength increases to 50. The 15 boss capacity they now have is no longer sufficient or cannot cater for their needs. Hence, there's a need to do what? To either do two things: get a bigger boss or get additional bosses. When they decide to get a bigger boss, the coastal bosses now that is able to take about 50 size of people, or that's able to cater for all their employees. What they've done there is what they call vertical scaling. Another example is you used to have your phone memory is of 16 gig today, but for one reason or the other it gets filled up. Instead of you going to buy another phone or another device, you decide to increase the memory size, buy additional memory size. What you've done there is vertical scaling. So in essence, you've been practicing, you're a system architect already, even before becoming a TPM. Alright. Now let's look at the advantage and the disadvantage of vertical scaling. One of the core advantage of vertical scaling is it's easy to implement. For you as a user, the only thing, you don't need to change your device, you just need to buy additional memory. You do not require any technical expertise to doing that. It's very easy to implement. Nobody has to write any single line of code to implement this. Very easy to implement, and it's pretty straightforward. However, the problem of single point of failure still exists. What do I mean? If the machine, either your database or the application server, decides to crash, nobody can use your solution. Your solution for that day or for that duration will become inaccessible. So it comes at its own cost. Secondly, in this session, we'll be looking at horizontal scaling. What does this mean? Horizontal scaling means adding more machine to share the workload. Let's bring this home. You remember the example of the staff and the boss we had explained. Instead of them getting a bigger boss now, the company decided to get additional bosses. That's literally what horizontal scaling means. Now let's look at the advantage and the disadvantage of horizontal scaling. One of the key advantages of horizontal scaling is it ensures reliability as opposed to having a single point of failure. If that lorry or that bus decides to break down, every member of the organization will have to find other means of transportation to get into their destination. But in the case of horizontal scaling, we now have multiple buses. We don't have single point of failure. So if one bus decides to go down, the other buses is still able to move people around. It's still able to cater to some staff needs, or it's still able to cater to additional staff needs. Also, horizontal scaling helps you to ensure that your system is built in a way to handle significantly high amount of traffic. When there's a traffic overload on a server, it's able to also route. You remember we discussed API gateway, where it's able to identify services that can route requests to efficiently and is able to get requests in real time. This can be done when you have horizontal scaling capability. So when there's a high inflow amount of traffic, it's able to scale up and scale down. Horizontal scaling helps you to ensure high reliability of your platform. However, there is this limitation. And what is the limitation of horizontal scaling? It's complex. When I mean it's highly complex because you have to have systems talking to themselves. Also, it's very expensive. Expensive to manage. It means you're able to manage about 4 different buses at the same times. In application terms, you're managing multiple databases. And when you're talking about databases, you need to ensure that data persists. There's something they call data persistence and data consistency in database. You have to ensure data persists across various databases or that you are setting up. When you're also looking at application as well, when you're scaling up your application server, you also need to ensure that the application server, you're able to service multiple application service at different times. However, there's a way that people do this, right? On system design where we have auto scaling, right? This works in a way where if a particular service is not being active, you can design your system in a way that it kills that service or that application. And it only brings it up when there's a need for it. But these are more advanced stuff. But what you're trying to say is managing scaling, horizontal scaling is very, very expensive and complex. As a matter of fact, it requires you to code in some cases. Thirdly, in this section, we'll be looking at load balancing. What does load balancing mean? We had mentioned load balancing around when we are looking at API gateway. But let's literally look at it in details. What does this mean? Load balancing is the process of sharing incoming traffic across multiple servers so that no single server becomes overloaded. Why is load balancing even important? You guessed it. It helps you ensure your system is reliable and it can perform. When there's a need for it to increase, it's able to cater for high traffic. Load balancing also helps you ensure that your system is able to perform and respond to customer in near real time. When I mean near real time, I'm not talking about 2 seconds, 3 seconds, we're talking about milliseconds. It helps you route your request to the server or the application that can quickly give your customer response. In this way, it also helps you ensure improved customer experience, both from the application level or from the API level. Think about load balancer as a traffic controller. Under load balancer, we'll be looking at load balancing strategy. There are 3 major types of strategy being adopted today. We have the round robin. What does this mean? This routes requests evenly across the server. Say you have 5 servers today, and you have 5 requests coming in. What this will do is it will route for server 1, it will route the first request to server 1, second request to server 2, third request to server 3, fourth request to server 4, fifth request to server 5. What this does is it ensures that loads are evenly distributed across the server. No single server is having to handle more than the other server. Requests are distributed evenly. List collection. What does this mean? It sends traffic. We don't forget we have said load balancer is more of like a traffic controller. It sends traffic to the least working server or application today. Say you have server A handling about 100 requests already, and we have server B handling just about 2 requests. Depending on your strategy, load balancer will route requests to the server B because it's handling the least connections or handling the least amount of requests. Thirdly, we have IP hashing. This is where we have client uses certain APIs or certain customers are mapped to certain application server. However, this has its own downtime. It means when that server is not available, the application experiences, the customer is not able to access the application. But people also use this as strategy. It ensures consistency. And this is where you also have certain information being cached in some certain application server. So look at what we have here. We have these are numbers of customers making requests. This is the internet. The internet here is serving as the device, whether they are making the request via API call, mobile application, tabs. And on this section, we have this is where the load balancer comes in place. It's able to route requests. And in this case, we have about 3 servers here. Depending on your strategy, load balancer will concur to the strategy you put in place. So under this section, database optimization strategy, we'll be looking at how you can optimize your database. We had said that every request you make at every given point in time talks to the database. It eats in certain requests where we had said is either reading, writing, deleting, updating a certain information. So every request, hypothetically, every request is expected to go into the database to fetch the information for the user. So there's a need for us to ensure that that database is optimized, or else we have data overloads. And when we have data overload, it will impact our infrastructure, it will impact our cost on the infrastructure level. You don't want to have a product that is generating revenue and you have the infrastructure taking the whole of the revenue. Yeah, the infrastructure should take certain revenue, but you should still have significant amount of your product revenue to yourself. So that's why it's important for us to look at database optimization strategy under system design. So for you as a TPM, while you're building your product, it's important that you have the database of your product is built in an efficient way. Firstly, we'll be looking at what is caching. We've discussed this concept of caching in some of our previous classes, but we'll reiterate it in this lesson. Caching is the technique of storing information in a short-time memory for easy access and quick responses. What does this mean? Instead of going into in your application or in building or designing your system, you can have 2 databases. You have the short database or the short memory database, and you have the primary database. The short memory database is where you store frequently accessed kind of information. Take your WhatsApp for instance. There are certain people today that since they downloaded their WhatsApp, their profile picture hasn't changed for about 5 years. These are types of information caching basically helps you manage or handle. The objective of caching is it helps you reduce latency, reduce database load, and also improve your system performance and scalability. Now let's look at caching strategies and types of caching. We have application caching, distributed caching, and CDN type of caching. But one thing I think I would like us to discuss here is caching strategy. The first one is time to life caching. These are the kind of shorter temporary databases that is time fixed, where you have situation whereby you want this certain information to be stored in the temporary database for 5 hours. After 5 hours, the system can delete it. Right. Secondly, we have write-through cache, and this strategy is used for where information is required in real time. Persistent databases. So instead of sending or saving that information, we had mentioned that you can create API or you can make update. Instead of creating an account or an information on the database directly, it sends it to the cache first. Then from the cache, it sends it to the database. What this does is it ensures system consistency, and you mostly see transaction or billing applications use this type of strategy because you don't want to make payment and instead of seeing 50,000 naira in your account, you are seeing 10,000 naira. That builds trust issue. But when you have write through cache, that information is currently in cache. It means the cache have the most updated data data or information about you or about your application. The third one we have is cache aside. So cache aside, the way cache aside literally works is where you have when you make an API call, the API call checks the cache first. If that information is not in the cache, it will route that request to database. Once that database fetches that information, before it sends that information, this can happen simultaneously. It sends that information back to the customer, and it also saves that information in the cache for subsequent or future use. These three are the most used common caching strategy. However, there are others, but these three are the most used common caching strategy. So the diagram we have here is for cache aside strategy, where the customer makes a request. Imagine we have an imaginary customer here. He makes a request. That request gets to the application server. What the application server does is where we have the host one, it sends that information to cache, or it tries to fetch that information in cache. In a scenario where that information exists in cache, it responds to that customer with the cached information. But in a scenario where the information is not in cache, it goes to the database to fetch the information. And once that information is being fetched, it sends it back to the customer. Right? On number 4, you see it persists by going to storing that information into the database cache. So for future requests, instead of going directly into the database, it goes into cache. What strategy is this? We just literally discussed the three major type of caching strategy. For my explanation here, what strategy do you think this is? You guessed right. Cache aside strategy. Secondly, we'll be looking at shredding. What is shredding? Shredding is the process of splitting data across multiple data nodes, where each node stores only a portion of the total data. Why is shredding important? Shredding helps you ensure that your database can scale horizontally. It prevents single database becoming a bottleneck, and it also helps you improve read and write. As your complaint grows, your need grows, your user base grows, your need for a larger database increases as well for efficient responses. Thirdly, we'll be looking at replication. What does replication mean? This involves maintaining multiple copies of same data across nodes. What does this literally does is it ensures data availability. And we've seen the common models. We have the primary replica and we have the multi-primary replica. And why do we even use replication strategy? Like I mentioned, it ensures high availability. It helps to ensure disaster recovery in a system where a single database is probably down, or it gets information, or the information in the database gets compromised. You have other database that can still provide you with such information. So your information, the customer information, is not lost in its entirety. We have it in other databases where you can go fetch it from. So it ensures data availability and help improving disaster recovery. Lastly, we'll be looking at indexing for performance. What does this mean? Indexing is the technique for allowing database to be found quickly without having to scan through every record. Let's use a typical example. Imagine you have a database with over 10 million users, and you're querying the database against your email address. Ideally, what it should do is it goes through each row of information to find. It goes through. Take for instance, your information is in the last database. When you have 10 million customers and your information is in the last database, what that is expected to do is it goes over 9 million records, one after the other, before they get to your information. What technologists have seen and have done is that this can pose a challenge and an overload on the database. What they introduce is indexing. And what does indexing does is it tells you, instead of having to go over the information one after the other, when you start typing the certain information, it brings out suggestions to you. And that's why you've seen the types of LinkedIn today. You go on LinkedIn and you search for Oluwole Ayeni. And just by searching Oluwole Ayeni alone, it starts bringing out suggestions to you. So it does not necessarily have to go into the database to start searching one after the other. So it brings out suggestions to you. We've also seen the likes of Facebook, Twitter, literally almost all companies uses this indexing, because if you're not using indexing, the amount of money you'll be paying on your infrastructure is going to be enormous. Indexing also helps you improve efficiency. And we had said that every call you make goes to the database. How do you ensure your system is able to respond in milliseconds? You have, or your application is able to respond in milliseconds. Indexing, obviously. So it's important for you as a TPM to ensure that when your engineers are building, they are building, or your database architect is structuring, it's able to factor in indexing to ensure you are able to build a system that is reliable, that can respond in milliseconds. And it will also save you a lot of money on the infrastructure level. Because as a TPM, beyond just your API being fast, your core responsibility is also to ensure that you build a system or an application in a way that it's cost effective for your system or for your business. Lastly, under this section, we'll be looking at latency and throughput and observability. Like we said earlier, the performance of your products, when I mean your product now, your API products, is measured on two major key metrics. First one is latency, second one is throughput. Now, what is latency? Latency is the time it takes for your system to respond to a request. It is measured in milliseconds. And the latency on your platform today, it directly impacts your customer experience. Let's take for instance, your payment API. We had mentioned payment API earlier. Your payment API that is expected to respond to customer in less than 100 milliseconds is now responding to a customer in 500 milliseconds. That's a major problem. Beyond just the metrics, it also helps you quickly, as a TPM, identify bottlenecks in your system. Secondly, throughput. What does this mean? Throughput is the number of requests your system can handle per second. It is measured as RPS, that's requests per second. It helps you quickly indicate and identify the capacity of your platform today. And it's also okay if your platform is designed to be able to respond efficiently to 100, or 100 is definitely small, 1 million requests per second. You can also have people build or optimize the system in a way that is able to handle 2 million requests per second. All of these are basically, they are trade-offs for you as a TPM in making decision. Whether you make it, the way you design to make your architecture or design your platform also has impact on the cost as well. And I think the best way for you to do it is look at the amount of usage you have on your platform and design, or the amount of usage you envisage on your platform, and design your system in a way that is able to cater for those needs. One key thing I would like us to take out of today's lesson is system design is not just a technical exercise for developers or for engineering leads. For you as a TPM, your understanding of system design helps you to ensure that you're able to build a solution or a platform that is reliable, that can stand the test of time, that is available, that can respond to customer in milliseconds, that can handle significant amount of traffic and respond in near real time. So for you as a TPM, system design is a decision trade-off for you. And the best platform that we've seen out there today design their system in such a way that it's able to do three key things. First is scalable, second is reliable, and it is highly responsive. I mean, it can perform under any circumstance, under any condition. Thank you for joining us today. See you in our next module.